Yeah. So still when it crosses 100, you can start now.
Okay, sir.
So how many people have registered for this event?
There are 250.
Around 250 faculty members from all over India, and also one participant from international level also brought here.
Okay. And should I keep my video on for the entire session, or just should I just share the slides?
When you start to share the slides, your video will appear as a small size in the corner, Professor.
Okay. So that means I should keep my video on for the entire duration.
Yes, yes.
Oh, that's fine.
Okay, Sushmita, you can start now.
Yes, sir. My warm greetings. I extend my warmest welcome to each and everyone invited here. I am Sushmita, doing my second year in the Department of Electronics and Communication Engineering at Chennai Institute of Technology. We are analog beings living in a digital world facing a quantum future. CIT, the college has not left any stones unturned in making its students worthy citizens. The time as a caterpillar has expired and the wings are ready. Yes, it is about transforming lives. It is indeed a privilege for all of us to get the opportunity of attending this webinar. To be short and crisp, yes, it is all about Knowledge 4.4. Today we have our expert, Dr. Dhiman Mallick from IIT Delhi, and our organizing secretary, Dr. Malati. I feel much pressure in welcoming you all. Now I request our organizing secretary to share a few words. Please, ma'am.
Good afternoon, all of you, dear participants. Once again, I am welcoming you for this afternoon session, fourth day of our FDP. Today we have our expert, Dr. Dhiman Mallick, with us. He is from Electrical Department from IIT Delhi. Today he is going to share the knowledge in the topic of powering of Internet of Things and energy harvesting and beyond. Actually, his areas of interest will be the MEMS, energy harvesting and all. I hope today we have the great session with us. Before going to the session, Sushmita will give small intro about our expert for our today's session.
Sure, ma'am. So, talking about our expert's profile, he is an assistant professor at the Department of Electrical Engineering at Indian Institute of Technology, Delhi. Before that, he was a postdoctoral researcher at Tyndall National Institute, Ireland. He received his BSc in Physics from University of Calcutta in 2007, followed by BTech and MTech degrees in Radio Physics and Electronics Engineering from University of Calcutta in 2010 and 2012, respectively. He received PhD degree in Electrical and Electronic Engineering from Tyndall National Institute. Till date, he has authored 35 published articles in reviewed journals and filed one patent. He received DST Inspire Faculty Award in 2008. Currently, he is working in the area of microsystem technologies leading to the autonomous operation of IoT. So thank you, ma'am. Thanks for giving me the opportunity. Thank you.
Thank you, Professor. Thanks a lot for accepting our invitation. You can take your session, Professor.
Thank you.
Share your screen.
Yeah.
Sushmita, you can turn off the video.
So can you see my screen now?
Yes, sir. Yes.
Okay. So thank you for the kind introduction, and thanks to everyone who have participated in this online FDP program organized by Chennai Institute of Technology. And it's a pleasure for me to talk about my research in this platform today. I hope everyone is doing well and safe wherever you are around the country or even outside. So today I will be talking about one part of my area of research. So the title of my talk is Powering the Internet of Things with Energy Harvesting and Beyond. So I am affiliated to Department of Electrical Engineering, Indian Institute of Technology, Delhi. So I work mainly in the area of MEMS or microsystems. So those who are not too familiar with this terminology, MEMS. So MEMS stands for micro electromechanical systems. So these are miniaturized systems which was first introduced in the 1960s, and then it got developed through the years. So it's integrate different electrical components and along with the mechanical components in the micro scale level for different functionalities. And with as the technology evolved, actually the not only mechanical, several other physical aspects also joined in with the electronics part that could we actually fabricate or develop in a semiconductor IC chip. So that's the basic about MEMS. So my research group is called Interdisciplinary Microsystems Lab, or IML. In our group, we work on three different aspects of this MEMS or microsystem technology, starting from the material integration. So we don't really work on the new material development or new material formation. Rather, we work on how the existing materials could be improved, they can be optimized, and they can be used for device applications. How they can be integrated in a CMOS compatible way into a MEMS devices, so that this device can be used in a bigger system. So the second stage is the device actual development of the device. So for that we do a lot of in-depth simulations. It could be multi-physics simulation. It could be some even material level simulations also. So at the device level, we do multi-physics simulations, numerical simulations. Then once we optimize the device structure, we go for microfabrication of the MEMS fabrication of the device. And ultimately, our goal is to characterize the device at a lab scale or at a real application field, so that we can benchmark or validate our device against our proposed theory or the with the aim that we started designing the device. And there is a third aspect of MEMS research also, where we also work in, though not that much actively, but it's a very important part, which is the interface electronics. So interface electronic means once we develop the device and once the device start working, you can't just use the MEMS device as it is for some application. So whatever raw data coming out of this MEMS devices, maybe it may be a sensor or maybe an actuator or maybe an energy harvester. So whatever raw data or raw signal coming out of that device, you need to process that signal. So for that, you need interface electronics. So that interface electronic has to be very focused on whatever application you are working on. So maybe it has to be very low power, it has to be energy efficient, it has to be volume efficient, it has to be device specific. So different kind of device has different requirement for its electronics. And ultimately, the complete system integration is our goal. So that's why we include that aspect of the research also within our area of work. Though in this area, we work actively with few of our colleagues who are expert in developing circuits, maybe analog or mixed signal circuits. So we work with them in collaboration. So right now, the focus areas of our group is first the energy harvesting, that I will be talking in most part of our talk today. The second part is wireless power transfer. That's a new upcoming area. The wireless power transfer is not a new technology, but for implantable devices, there are a lot of limitations. So how you can overcome those limitations using your micro or nano systems approach, that we want to explore. Third is right now there are a lot of work going on in the area of neural interface devices. So we are also seeing how we can use this MEMS technology for using it as a neural interface device. And third is the low power sensing, microfluidic sensing devices, which have a lot of health related applications. So we have started working on that area also. Okay, so today, as I said, I will be talking mostly about this energy harvesting area. So what is actually energy harvesting? So some of us may be familiar with this term. Energy harvesting means generating electrical energy from some other form of energy. Okay, but this energy harvesting is actually nothing new. It's not a new as a concept. So this wind turbines or windmills are existing over centuries. So this is an very old wind power generator in US in the 1800th century. So that's a not new technology. So maybe it's a bigger device or bigger thing that is shown here in the picture, but it's as a technology or as a concept, it is not new. So why are we suddenly interested in this century-old technology then? So I will be coming to that, but let's come bit ahead in time. So in the recent or over the last few decades actually, we have seen wristwatches which rely on the manual powering, where you use the mechanical powering and you use a rotor to store energy in the spring, and as the spring release this energy, some electrical mechanism gets charged. So Psycho actually has this kinetic range of wristwatches available over very long period of time. So it is also not a new thing. So it's available within the wristwatch level also. So it's not just available in the windmill level, it's also available at the wristwatch level. So this powering of devices from external energy sources is not a new as a concept. Then why we are suddenly interested in this technology? Why so much work is suddenly going on in this energy harvesting area over last 10 years or 15 years? So there is a reason behind it, and the reason got actually very strong in the last 5 to 10 years. So the reason is the emergence of this IoT or Internet of Things technology. So we, some of us also have heard of this technological platform, this Internet of Things. So what is it? So here we consider that like our internet, all the physical object around us or in our surrounding world will also be connected to a central internet hub. So why, and it will be connected wirelessly. So why it is so important? Because ultimately what we want to do, we want to gather some information about our regular objects. So the regular objects could be a tree outside your house, it could be a door at the entrance of your house, or it could be some gadget within your house. So these are normal things, but we want to gather some information out of this thing, normal things, so that we can make decisions. So this decision making is actually very important. So once we have this decision making ability, we can make things smart. So now we have smartwatch, now we have even smart gadgets like or smart appliances like the smart TV, smart refrigerator, those things are available. So what is meant by smart? They provide information. The smartwatch gives you a lot of information or data. This fridge, refrigerator now gives you how long it can cool a thing. You can operate it remotely. So once you have this information available at your fingertip, you can do a lot of things. So this decision making capability is actually very important, and that is possible through this Internet of Things technology. So here we consider that internet is connected to our physical world using wireless sensors. And as I said, in the last 5 to 10 years, this Internet of Things, we have seen a boom in this technology area. And as it is predicted that in the next few years, or as it is going on right now, this number of connected things within Internet of Things technological platform is going to be very high. So it is going to be around 10 billion in the next 5 years or so. So once it does, so what is the human population on Earth right now? So maybe it's 7 billion or something. So it is going to cross the overall human population on Earth in some year of time. So then the question arises, so there are a lot of challenges. So when that thing will happen, so we have to be ready for that. So I will discuss one particular challenge associated with this IoT technology. But before going into that, just let us take a look at the anatomy of this one of the IoT devices. So these different IoT devices, basically these are wireless sensor devices. So how their structure looks like? So they consist of some sensor devices which actually extract information from your environment. This information could be temperature, position, navigation status, or anything, light or whatever. So this sensor gathers those information. Then there is a low power microcontroller system that process this information, make it into a useful data. And third is a RF transceiver. So what does RF transceiver do? it transmits the data from the IoT device to a central hub or to some other IoT devices. And it also receives the information from the other devices. So the challenge, one of the main challenges, all of these three units require their power to work, require some power to operate. Now that it is fine, it was fine till we had some few devices like this. Wireless sensor nodes are also available over a long time now. So it was fine until we had few devices like this available. But when we are considering 10 billion such IoT devices, we need 10 billion power source to power these devices. Now, how we will power? So is it possible to make these devices self-powering? So if we can do that, then we can have a lot of advantage. So what are those advantages? First thing, how you conventionally power these devices? You use batteries, right? But there are problems with batteries. The main problem is this battery's power. So you can think of your smartwatch also. So once you charge the smartwatch, as you keep on using it over a few hours or within a day's time, the battery capability drops, your charge drops. So you have to recharge this device. So now this is true for any kind of batteries actually. So the battery performances drops over the time. Now the thing is, you can't recharge all of your 10 billion IoT devices periodically over time. So what's the solution? So you need to replace it or reinstall it. So if you want to do that, you actually need a lot of manpower, lot of logistical power investment. So that's not a feasible solution. So we can say that the use of battery to power IoT devices is not a very feasible solution. Or in other words, we can say that these batteries are not suitable for feed and forget applications like this IoT. So the alternative is to harvest energy from our surroundings or the sensor surroundings. So there are few technologies available for energy harvesting from ambient sources. These are solar energy harvesters or solar cells, thermal energy harvesters or thermoelectric generators, RF power harvesters which generate power from RF signals like mobile signals, and lastly the mechanical signals or mechanical vibrations that is available around us. From that mechanical energy we can harvest energy, so that is called the mechanical energy harvesting. So these four are the main four domains of energy harvesting devices. So now a lot of work has already been done in the solar area, and a large number of researchers are actually around the country or around the world are working on this solar cell efficiency improvement and developing new materials for solar cells or photovoltaics. So solar cells is a very mature technology, and solar cell is actually good as a renewable energy source. But there is a difference between renewable energy and energy harvesting. So I will explain that in my next few slides. But for small scale applications, solar cell is not so good, particularly if you are considering your portable electronics or embedded electronics which you will embed within your body. For those applications, solar cell might not work that efficiently. Second is thermoelectric energy harvester, which works on Seebeck effect. So that's one area also some work is going on. But thermoelectric is also dependent on the temperature difference between the two sides of the devices. So now when you consider a very miniaturized device, maybe a micro scale device, to maintaining a suitable temperature difference to generate some useful electrical energy is not always possible. So thermoelectric also have some limitations. Third is RF. RF is also good, but again RF works on the antenna that you require for RF energy harvesting. It is also called the rectenna, that comes with antenna and a rectifier. So this rectenna length, physical dimensions are normally very large. So you can't make them miniaturized for this kind of portable or embedded electronic applications. So it has also some limitations. The fourth is this mechanical vibrations or mechanical motion that is available around us. So that is actually a very suitable area for this miniaturized energy harvesting work. Why? Because this mechanical vibration or mechanical motions are available all around us. So you can think the most simplest form: when you walk, your hand moves, your knee moves, jerks, your leg moves, even all the time your heart is pumping. So all these forms are generating some mechanical energy. So if you can extract some electrical energy out of this mechanical form, then you can use it for some useful applications. So it's not just true for human body, it's actually true for any form of application you can think of. So maybe in automobile, when a car moves, there are a lot of engine is shaking or vibrating. Then the plane movement, train movement, any kind of movement, the industry-based machine movement, equipment movement, all this generates some sort of vibration or mechanical energy. And transforming the mechanical form of energy into electrical form actually comes in right into the domain of MEMS. So the MEMS name comes from exactly electromechanical system. So the energy harvesting, mechanical energy harvesting is very suited for MEMS related work. So now, before going into the further details, so we are talking about this wireless sensor node, which is the heart of any IoT devices. So let's just think of how much power you actually need to operate a wireless sensor node mode. So this is actually a Telos B mode, which is developed by UC Berkeley, and Texas Instruments actually commercialized it later. So this is a very standard wireless sensor mode. It is actually open source and available for researchers to customize it. So how much voltage it requires, or what inside it, what it has? It has 2 light sensor, 1 temperature sensor, Zigbee transceiver, super capacitor, or an ADC controller which monitor a supercapacitor voltage. And what is required from the outside? It requires a constant supply voltage of 3 volt, and it has an active mode. So how this wireless sensor node works, so it doesn't sense all the time. So it becomes active for a very short amount of time when it senses, like shown here in this diagram. And rest of the time it remains in the sleep mode when it doesn't sense anything. But this sleep mode also needs some power, some current to maintain the sleep mode of operation. So like it's for example, here it requires around 12 microamp, whereas when it becomes active, when it is actually sensing, it requires a very high current. It requires almost 20 milliampere of current. So if you calculate the average power required by a mode over a hour of time, considering that this mode become active only 2 times per hour, then the average power requirement comes out to be 46 microwatt or around 50 microwatt. So this is actually the kind of range of power that is required by a wireless sensor node mode. So we can consider it from 0 to 100 microwatt, or maybe a few hundred more microwatt. That is the power required by a WSN. So let's try to put this information more clearly on a graph and compare it with some of the energy harvesting technologies. So on this green arrow, what we have shown is different power level, and those power levels are actually the power required by different kind of devices. So at the lowest of it is the 10 nanowatt, which is the power required by a vibration sensor or a mechanical sensor. Then a quartz oscillator need around 100 nanowatt of power. Pocket calculator may be needing 1 microwatt power. A smart card or a RFID tag requires around 10 microwatt power, and so on. So later on, all this communication techniques like this low energy Bluetooth Zigbee required 10 milliwatt of power. Then your GSM mobile phone requires an average power of 1 watt. Your laptop requires 10 watt of power, and so on. So the operation range of many IoT device actually falls within this range. So it few tens of milliwatt to few tens of microwatt, this range. So if you can generate any amount of power within this range, you can operate your IoT device using your energy harvesting technology. Now on this y-axis, which is the battery runtime, so this actually shows just by using your battery, how often you need to recharge or recharge your battery without for operating these devices. So for example, at the top of it is in hours, so that comes near that map with the desktop, laptop or mobile phone. So your mobile phone or laptop, you can work for only few hours without recharging it. So after few hours you need to recharge it. So that's how the mapping is done. And on the bottom side of it, if you see some sensors or even these low power IoT devices, you can operate them using battery for few months at least. So that at the very bottom of it, it's in years. So somewhere here it will be few months. So just by using battery, you can operate these IoT devices over a few months of time easily without needing to recharge it. But this sensor devices or IoT devices that we will embed in our application area can work over a few years or maybe 10 years of time. So we are not happy with a few months of time. We want to augment the lifespan of our battery. We want to use this, make continuous supply of power to these devices without needing to charge them back again in a few months time. So that's why this energy harvesting is useful. So here in different coloring, what we have shown here is in what range these sources generate power. So for example, this mechanical sources like mechanical energy harvester generate power in this range, can generate energy in this range from 1 milliwatt to few microwatt of energy. So at the lower end, it comes thermal sources, and at the very low end, it comes the radiant sources like RF or some sources like solar energy, like indoor operation or the outdoor operation. But you have to remember that when you consider the energy density that you get out of these sources, actually nothing can overcome the solar cell when it operates at the outside, that is directly under sun. It has the maximum of energy density. But in most applications, or in many applications, you don't get that opportunity to work under the direct sun. So what are the other alternatives? So we see that if we compare the energy density, the vibration or the stress strain based mechanical sources, they have also very good numbers. Thermal also have good numbers, but they, as I said, you need to maintain the temperature gradient. That is also always not feasible. So if you see that the mechanical sources are actually very good for this miniaturized energy harvesting application. Okay, so now coming to the theory of energy harvest, mechanical energy harvesting, or we can also call it a inertial energy harvesting system. So how the entire system looks like? So you have some ambient mechanical source like ambient vibration. To transform this mechanical energy into electrical form, you need a mechanical to electrical transducer. So that's actually the MEMS part, how you develop this MEMS device. And once you have your electrical signal here or your electrical power here, that's actually AC power. You need to condition or you need to process this AC power into a usable form of electrical energy. So as I shown in previous slides, that this wireless sensor node requires a constant supply voltage of 3 volt, maybe of 3 volt, maybe of 1.5 volt, or some other voltage, but it needs a regulated supply of some constant voltage. So, and this electrical signal is actually constantly changing. It's first of all, it's AC and it's constantly changing because your incoming mechanical signal is changing. So this electrical signal produced here is also changing. So that's why to process your incoming electrical signal, you need a power management unit. So in this case, this interface electronic circuit is called the power management system. So what it will need? It will need a AC to DC converter or a rectifier to first of all convert the AC signal into a DC. Then you need a DC to DC converter so that you can either maybe if you work on the boost mode, you can uplift the DC level, or you can lower down the DC level by using a buck converter. And after your DC to DC converter, you need some kind of storage mechanism like a supercapacitor or similar things, or some capacitor to store the energy. And after that, you also need a regulator, voltage regulator, so that you can actually get a regulated supply at the output or at the load, which you can now use for your application. Okay, so as I said, I am collaborating with some of my colleagues regarding this part, this power management unit part. I mainly work, or in my group, we actually work mainly on this mechanical to electrical transducer using MEMS devices. So what are the research challenge in this area? So the main challenge is, first of all, is the power density. So for this energy harvesting, you need to produce more power and you should take small space. So that's the main thing. So that's why power density, maintaining good power density is a big challenge. Second is the bandwidth. So it is difficult to understand just if I just say now, but we will be discussing elaborately about this. Third is the reliability. So when you are operating your device under some mechanical excitation, reliability becomes a major issue. So your device has to be very reliable so that it can operate over the years of time. And fourth is the feasibility. So how feasible it is for some specific application. So in some application scenario, maybe the mechanical excitation that you get out of the source is not that strong. It is very weak mechanical excitation. So your device may not produce some suitable amount of electrical power at the output. So you have to consider the feasibility of a device for a specific application, and you also have to remember that you must produce a AC voltage here which you can actually rectify. Unless you are able to rectify your AC signal, you can't further process it, and then your device is of no use. So considering the source side to see how much mechanical excitation it can produce, and considering the interface side, where you have to consider that your interface circuit should be able to process your incoming AC signal, are the two main constraints for developing this mechanical to electrical transducer or the MEMS device. So this mechanical to electrical transducers, which is the basic of our inertial energy harvesting or mechanical energy harvesting, is basically modeled using a spring mass damper model. So, so I was saying that this energy harvesting is different from renewable energy sources, in the sense that in renewable energy sources, like in windmill or wind turbine, you have one of your end is anchored to the ground, to the earth, and there is a large structure above it. In energy harvesting, you do not get that advantage. Energy harvesting is very localized, right? You are trying to embed your device into some chip along with other components, and so there is no points to anchor your device to the earth. So that's why you need to follow some other rule. So what is that rule? You need to have a model like this. So what is the advantage of this model? Here, instead of having this ground anchoring, you create a frame, and in this frame you anchor your mechanical spring that you can fabricate using your MEMS technique. So once you do that, you can actually replicate the scenario of a renewable energy system within a very small scale, in a very localized manner. So in that sense, the renewable energy sources and energy harvester are completely different or somewhat different. So now once you have this frame and you connect a spring with it, then at the end of it, there is a proof mass connected to it, which can move as you have an input vibration applied to this frame. So because this frame is now fixed, the spring moves. So due to the spring movement, your mass also moves. And then you can have a transducer associated with this model, which can transform the mechanical energy into electrical form. So there will be two types of damping associated with this model. First of all is the mechanical model. So whenever cantilever or some kind of a spring structure move, there will be air drag or air resistance. So that's actually the main source of mechanical damping. So that thing is there. And the next damping is your electrical damping. So whenever you associate some transducer along with this model, you will have some electrical energy that is being damped. So basically, you are taking out electrical energy out of this system, right? So that is the energy harvesting. So when you are taking electrical energy out of system, so that also acts as some kind of a damper. So that's we call the electrical damper. So there are two types of damping: mechanical damping and electrical damping. And so together them we can all call it the total damping, which constituting of Cm and Ce. So the basic equation of motion for this kind of system is given by the second order differential equation. And so here you see that this damping term comes with the velocity. So it is also called the velocity damped resonant generator, or VDRG. And from this model, actually, we can calculate how much power you will be able to extract in your electrical damper, which is given by these equations. So we see that it depends on some factors. So first of all, it depends on your proof mass. Your proof mass, it is depending directly on your proof mass. Secondly, depending on your electrical damping term. So for example, rho E in this case. So this electrical damping plays also a very important role. So it depends on R. R is given by your omega by omega n. Omega n is the natural frequency of your this spring system. So it depends on the operational frequency and the natural frequency of the device. And fourth, it depends on the input force, input mechanical force that you are applying. On that, it depends. So it mainly depends on four factors. So from this equation, what we can see that the maximum power occurs at resonance. So it is a resonant system. Here, the maximum power occurs when your incoming frequency matches with your natural frequency of the system. And so then in that case, the maximum power occurs. And this power is proportional to the proof mass, as I said. It is proportional to a square divided by omega. And if we try to calculate the maximum power with respect to this electrical damping, we find that the condition for maximum power is when your electrical damping term is equal to mechanical damping. So when you can match this electrical damping with your mechanical damping, then you can get the maximum power extracted out of the system. So the tuning term in this case is the load resistance. So you always apply a load resistor at the output of your device to and you can change that load resistance. So that's the only tuning parameter you have, by changing which you can match your electrical damping with your mechanical damping to get the maximum power. Okay, so as I was saying that this electrical damping plays a very important role. So you can think of as in terms of Q factor also. So we know about Q factor. So here we have plotted some normalized power with respect to the ratio of electrical Q factor divided by the mechanical Q factor. We see that the maximum power is coming out when this thing is matched, as I said, or when this ratio is 1, then we get the maximum power. But the important thing to note here is that in practice, we never actually is able to operate at this point. We mostly operate in this region. Why? Because this electrical Q factor or your electrical damping depends on a term called the electromechanical coupling. So electromechanical coupling depends on your transducer type, how your transducer work. On that, your electromechanical coupling term depends. But in practice, your transducer is never so efficient that you can reach this point. So mostly you operate in this lower region. Okay, so to improve this electromechanical coupling down, you need to work on your transducer. So now we will learn about the transducer. So there are mainly three type of transducer mechanisms that are used in MEMS for this energy harvesting activity. So first of all is the electrostatic, which works on the changing capacitance of charge plate mechanism. So for example, in your MEMS, if you consider two sets of electrodes which are pre-charged, and so that they have some finite capacitance between them. So now if you start moving one with in relative to other, then what will happen? So due to the change of gap between the two electrodes, your capacitance will change, and change of capacitance means your voltage will change. So you can generate some voltage due to this movement. So that's the mechanism of electrostatic transducer. So advantage of this technique is it is suitable for MEMS. So it is very easy to develop some MEMS-based electrostatic generator. But the problem is it requires a biasing voltage. So as I said, it needs to be pre-charged. So that means it needs to be biased. So you need to provide it with the biasing voltage. So that's a major drawback, and the output voltage that you get is actually also not so high. So you are giving high biasing voltage, but you are not getting enough output voltage out of the device. So that's one of the main challenge of electrostatic transducer. Second is the piezoelectric transducer. So here piezoelectric materials are some form of active materials, where you have charge displacement or charge separation as a result of mechanical strain. And as the charge gets separated into the two ends of the material, you get electric potential out of the material. So electrical potential difference is created, that is the output voltage that you get. So that's the piezoelectric material. So piezoelectric material are not so easy to actually develop. You can develop it using MEMS processes, but often maintaining the high piezoelectric coefficient is not so easy. So that's the challenge. But the good thing about piezoelectric material is or piezoelectric generator is that the entire processing is also very much CMOS or MEMS compatible. Second thing is it can produce very high voltage, but on the contrary, it produces a low current. But high voltage is what you need. You need to rectify your AC signal. So for that, you need to have a very high voltage from a very tiny mechanical excitation. So that is possible using your piezoelectric energy harvester. And piezoelectric energy harvester, the disadvantage is that because it works on the charge separation mechanism, it has this very high capacitance associated with it. So the main impedance is dominated by the capacitance of the piezoelectric material. So that's a drawback, or that's a challenge for designing the circuit part of this piezoelectric energy harvester. Third is the electromagnetic energy harvester, which works on the Faraday's law of induction. That is, we know that when there is a relative movement between a magnet and a coil, or when a conductor actually moves through a magnetic field, then our electrical potential difference is induced within that coil. So by using this principle, we can design our electromagnetic mechanical energy harvesters. So the advantage, first of all, of this technique is that it do not require any extra component like your electrostatic. in electrostatic, you need to provide this biasing voltage. You do not need such thing in electromagnetic. The good thing about it is that it produces high current, so that may be a good thing. But the drawback is that it produces a low voltage. So the voltage that is induced in your coil is not so high. That is another reason, is that the coil normally have a very small resistance, so that's why you cannot have a very large voltage across the coil electrodes. So that's a problem with the electromagnetic generator. And actually electromagnetic generator, when it's scaled down to MEMS scale, the voltage gets lower and lower, so that's a big challenge. And the integration of electromagnetic generators is also very challenging. Developing efficient coil at the MEMS scale or micro scale is challenging. And the second thing is integration of the magnets is also a very challenging task in MEMS. It also, the magnets are also useful in other applications of sensing and in microfluidics devices. I will be discussing a slide on that also. But in general, the integration of permanent magnet, particularly at the MEMS scale, is very challenging. So in our group, we work on different transducers for energy harvesting activities. So mainly we will work on piezoelectric and electromagnetics and their associated challenges, associated materials, associated electronics. We work on those things. So this is a typical MEMS piezoelectric energy harvester that is fabricated using MEMS techniques. So what we did is we investigated different topologies of the mechanical spring or the mechanical cantilevers, like trapezoidal beam, which is shown here, or maybe a rectangular narrow beam, rectangular wide beam, and so on. So we investigated different beam topologies, and finally what we optimized is that this trapezoidal or tapered shaped beam is actually very useful or most efficient for piezoelectric transducer building, because this trapezoidal beam can produce maximum amount of stress near the base of the cantilever compared to your rectangular or any other form of structure. And the more stress you generate, normally on top of that, here we have deposited our piezoelectric layer. So the more stress you can generate here, you will be able to extract more electrical voltage out of that device. So here, for example, we have shown the characteristic or the experimental characterization of 3 different types of beam structures. So first of all, their frequencies are different due to the different physical structure and physical dimensions. But what we see that the trapezoidal beam has a very kind of high voltage, though it's not determined at the exact same level of mechanical excitation, but the trapezoidal beam has a reasonably good output voltage. So this is the one of the most optimized structure for MEMS piezoelectric energy harvester. And we have used here the aluminum nitride piezoelectric thin film, which is deposited using sputtering process. So that's a reactive sputtering mechanism we have employed to develop this highly C-axis oriented aluminum nitride piezoelectric film. So we are working on actually other type of piezoelectric materials which can be developed using chemical synthesis routes also. But the piezoelectric coefficient found in this sputtered aluminum thin film is actually the highest. So we take that material as our standard for developing this piezoelectric energy harvesting devices. And this is the typical frequency versus the output voltage. This is the open circuit voltage curve for this different beam structure of energy harvesting devices. So we see that they are very high Q structure, that is they are strongly resonant, they have a very sharp resonance peak at their typical resonant frequencies. And then these devices are operating
at frequencies in the range from 90 hertz to 150 hertz or within 200 hertz. So this is the range where MEMS technology can reach actually very easily. So you have to think about this fact that as you scale down the physical dimensions, your frequencies actually go high. And actually the normal trend in MEMS or MEMS devices actually is to go smaller and smaller so that you can have higher and higher frequencies. Normal resonators or oscillators work on those frequencies only. But for energy harvesting, you have to go lower in your frequency. So most of the available mechanical vibration frequencies like machine vibration or human motion vibrations, they are actually in the very low frequency range, even in the range of below 150 hertz to below 20 hertz range. So using MEMS technique, it is convenient to go around this frequency range very easily. To go beyond that, you need to develop further advanced processing techniques. So we are working on those techniques also. But this is what we have achieved already. So we can safely work with below 200 hertz easily. So this is the power output versus the load resistance plot. So as I was saying that load resisting is a tuning parameter. You can change your load resistance to optimize the electrical damping term, and by optimizing that you can get the maximum power condition. This is what is shown here at a one particular load resistance. You get your maximum power out of the device. As you keep on increasing the load, your power decreases. So load resistance is a very good tuning parameter for extracting the maximum power. This is, as I said, that this is a very resonant curve, and as you change the quality factor of the device. So again, we go back to the theory. As you change the quality factor of the device, as you reduce the quality factor, you actually go from very resonance kind of behavior to a kind of a wideband behavior. For example, this green curve is quite wideband. But on the contrary, your power is reduced, so you can't have a very low quality factor device also. So you can work at a very wideband operational region, but your power will be reduced. So that's the second challenge. You remember I said that the bandwidth is a challenge for energy harvesting devices. So this is the reason. So you need to have a wide bandwidth, but if you reduce the quality factor, then your power will be reduced. But why do you need to have wide bandwidth? So let's go back to some application theory again. So if we characterize the different mechanical sources available around us, maybe from human motion or from some machine vibration or some train movement or aircraft movement or whatever. So if we characterize them, we'll see that only 23% of the sources that have singles dominant stationary frequency, for which you can employ a very high Q resonance type structure, and that will effectively extract the energy. But most of the sources are broadband. That is, they have either multiple peaks within their spectrum, or they are very noisy, or they may be they may have the single dominant frequency only, but that is not stationary. That is a non-stationary frequency and changing over time. So if you design your device that operate only at one particular frequency, it will not be able to extract the energy efficiently out of those systems or those mechanical excitation efficiently. So what we did is we go back to our equation of motion again, and instead of considering just a linear spring force, which is given here, which we call the linear spring force, we take a generalized spring force and we extend in terms of power order. So instead of having just a linear term, we introduce some higher order terms, and higher order terms in terms of this cantilever displacement. So X is your cantilever displacement. So in terms of that, we introduce a higher order terms in the MEMS structure topology. So what it does, what this nonlinear spring force does to this equation of motion. So if you now have this equation of motion with this nonlinear spring force, your frequency response will actually be completely changed. You will not get a linear frequency response like this. You will get into the nonlinear dynamic range of operation, and your frequency curve will get this kind of tilted, and you will get a very wide bandwidth of operation from your device. So that's actually a good thing. Then once you get this wide bandwidth of operation, you can address this 53% of the sources also efficiently, because if your source of mechanical excitation falls within this operational region of the device, then you can now effectively extract the electrical energy from the mechanical side. So how to do that? So we did that using for electromagnetic transducer device, but you can do that using piezoelectric or electrostatic equally well. So this is another type MEMS electromagnetic energy harvesting device that we have worked on. But instead of a high Q resonant device, this is a nonlinear device. So how it is nonlinear is due to the spring structure. So this spring structure is designed in such a way that it is instead of giving this kind of linear spring force, it is giving a higher order terms in the spring force factor also. And so your spring structure is itself is nonlinear. And when we characterized it, we also got the kind of nonlinear frequency response that we were expecting. And this nonlinear wideband of operation actually keeps on increasing as we go on from 0.1G to 0.2G to 0.5G. So as we keeps on increasing the input acceleration level, our bandwidth of operation actually increases. At very low acceleration of operation, it behaves like a linear device only. But as you keep on increasing the acceleration level, the frequency curve become more and more tilted, and then you get more and more bandwidth out of your device. So this is MEMS implementation of nonlinear electromagnetic energy harvester that we have worked on in our group. So far we have discussed about different MEMS implementations of energy harvesting device and why you need a nonlinear technique to get the wideband of operation out of your device to address different application scenarios. So for benchmarking these devices, in particular any energy harvesting, mechanical energy harvesting devices, we have a figure of merit which is called the normalized power density, which is given by this formula, that is given by your power divided by your acceleration square. Acceleration comes in the form of square in the power formula. So if we go back to our initial power equation, maybe see it comes at the a square. So that's why you have taken as the a square and divided by the volume. So density means it will be always divided by volume. So you define a normalized power density figure of merit for the mechanical energy harvesting devices. And we have plotted this figure of merit in terms of both volume as well as in terms of the frequency. So, and we have benchmarked some of our devices. But you see that when it comes to the volume, our device is actually working very well. So we have a or more or less small volume of 10 to the power minus 7 meter cube. So and that range we have one of the top normalized power density. In terms of the frequency, we can still improve when we are trying to do that. But still, whatever the other reported frequency of operation of the other devices are, our device also shown a good normalized power density compared with the reported ones. Okay, so now comes to the important discussion of scaling. So when you are going to MEMS scale, that means we are scaling down our devices to micro scale. So we are scaling down. So what's the challenge then? So first of all, let's talk about the advantage. The MEMS actually reduces cost, because in MEMS scaling you develop maybe hundreds or thousands of devices at one fabrication run. So you can produce multiple devices using single process. So that's how MEMS can reduce your cost, but there is a trade-off between the size and the effectiveness. So these are some of the reported energy harvesting devices that are developed using conventional machining. That is, those are developed using conventional processes like CNC machining, laser printing, those kind of things. And these are the devices that are developed solely using microfabrication processes. Now, if we compare the normalized power density for all of these devices, we see that for MEMS, the volume is definitely small, but the normalized power density is also very small. So our target is to move in this along this red arrow, not along this blue arrow where we are currently. This is the state of the art. But if we can somehow reach there, that is, we have the small volume, but we have a very good normalized power density, then we can make effective use of this MEMS energy harvesting devices for the proposed applications. So that's the one of the main challenges. Okay, so now go back to the theory again. So we are talking about the scaling, but technically how much output power we can get. So that is actually unbounded. So if you see this formula, this power formula, you can get actually an enormous amount of power out of your MEMS device. But then what is the limitation, or what is the restricting factor? The first restricting factor is that this theory, what the initial theory that we talked about, it assumes that your force, a vibration source, is exerting a constant force, or exerting the constant supply of mechanical energy to your device throughout the operational period. But that is actually not true. Your mechanical source may not be active for some duration of time. So then during that time, actually your device will produce no power. Now, if you take the average power, you have to take account of those time also when your device is not working. So then your average power actually reduces substantially. And second assumption that it made, that the proof mass displacement is unbounded. But that is also not true. So here we talked about the device volume. So what is device volume? Device volume is your device plus your the frame, outer frame that you have, the packaging that you have, all those contains the device volume. So for example, in this case, your this spring structure can't go beyond this PCB. So your displacement must be restricted up to this bottom layer. So it can't go beyond that. If your displacement cross this, it will hit the bottom layer and it might cause accident, or it might cause a destruction of the device. So this proof mass displacement is unbounded. That theory is not correct. So these are the two practical limitations that you have compared to the theoretical study that we do in realization of a practical device for any application. Now, since we know what is the limitation, now let's take an example to understand this more clearly. So let's take an example for a body on harvester. Maybe let's consider that you are wearing an energy harvester in your belt. And this, what is this harvester? This is a very hypothetical harvester you can consider. Let's consider that it is in the size of your iPhone, maybe old iPhone, maybe iPhone 6, which has a mass of, say, for example, 173 grams. Now you are walking, your walking frequency is 1 Hertz, so you are walking at that frequency, and your harvester is continuously shaking at that frequency. And when you are walking around your belt area, the mechanical acceleration that you get is 0.5 g, or 5 meter per second square. So that's the kind of external mechanical excitation that you get. and we assume a reasonable quality factor, like matched quality factor of 20 and 20 for both mechanical and electrical domain. And we assume that we operate with a resonance-based device and our resonance occur at this 1 Hz. So using this power formula, we can calculate what is the maximum power that we can get. So this is enormous. This is 1.7 watts. In your initial curves, we say that in order to run your mobile phone, you need in the order of 1 watt or in the watt range of power. So we can then get watt range of power from our built-on harvester, right? But this is not correct. Why? Because there is a very misleading concept hidden in this calculation, and this misleading consideration is that we have considered our motion is unconstrained. So if we find out the motion of our proof mass, we can calculate it using our initial theory. We will find out that this Z0 of the proof mass displacement required to produce this enormous amount of power is actually 1.27 meters. So you need to have a device which can move up to 1.27 meters in order to produce this 1.7 watts of power. So that's not a practical solution, right? You can't have a 1.27 meter long device in your body to produce 1 watt of power. Your devices are very small. If not MEMS, it may be millimeter scale. So that's also very small. So your motion is restricted. So you can't go beyond motion range, and that's why you can't produce power at your will. So even we can say that even if there is a lot of power available within your device, but you can unfortunately it requires a very large displacement to produce those power, and therefore it is not a very feasible solution. Okay. So that's why this scaling is a very challenging aspect for mechanical energy harvesting devices. Now come to the some more perspective. So this is actually taken from a paper, this reference. So here what is shown is, so we have considered two frequencies, so 1 Hertz and 10 Hertz. So this is the normal human movement or human body movement frequencies. And for different volume, it is at this frequency what level of power can be harvested. This is a rough estimation has been done. So these two lines, this blue line and this purple line, shown these two curves. The blue line for the 1 Hertz and the purple line for the 10 Hertz. This two shows the power you get for different volume. Now in the same curve, what is shown here, these 4 points are the power requirement by 4 different devices. So for example, this blue dot is your laptop, which has a volume more than 100 centimeter cube, quite bigger than 100 centimeter cube, and it has a power requirement, very large power requirement. Similarly, in the same plot, the second comes the red dot, which is for the cell phone, whose volume is less than 100, but it still has a very high volume. And these two are your wristwatch and a sensor node. So, okay, so let's see. So your laptop, or using your laptop, your power requirement, you see that it's very high, but how it compares to the generated power at 1 Hertz and 10 Hertz, your body on energy harvester. Again, this is a theoretical study. It is not a practical study. So, so for that, we see that it is possible. It is possible to generate that amount of power using your energy harvester to run your laptop. But for that, your harvester size also should be comparable to your laptop size. So then it's become unpractical. So you can't have a harvester size of your laptop tagged along with your body to power your laptop. So that's not a feasible solution. The same thing is true for the cell phone also. But when you go down in size, when you come below 1 cc or even lower than that, we see that this harvester is clearly winning. Harvester line is way above your this wristwatch or the sensor node. So wristwatch is, that's why this energy harvesting power wristwatch is already available in the market for some time now. So that's the reason of success behind this. And now the sensor node is also looking very good, because you can harvest, at least theoretically, you can harvest enough power so that you can power these sensor nodes using 1 hertz or 10 hertz harvester. So if you keep on increasing this frequency, this line will go up and up. So the sensor node is looking good, and this is the main application area where we want to focus. So our focus area is to power the sensor nodes. So this sensor node is looking nice with respect to the generated power of a energy harvester. But we want to compare our energy harvesting capability with ultimately with the batteries, because we want to replace batteries. We want to compare our capability with the batteries. So how does it compare? So we have taken the same curves here. We have taken the energy harvesting at 1 hertz and 10 hertz curves in this. But along with that, we have now plotted the power that you get out of the battery along these dotted lines. So there are 2 dotted lines. One is in green and one in this gray. So the green line is batteries which need to be charged in every 1 month of time, and the gray one is the battery which need to be charged in every year time. So battery normally gives you energy, not power. So in order to get the power out of the battery, you need to divide it by the time. So that shows that when you divide it by the month time, the power is high, and when you divide it by a year time, the power is low. So for applications where you need to charge your battery more frequently, for example, in the case of cell phone, this line will go, these lines, battery lines will actually go up and up. So it will go above again your energy harvesting generated power line. So that's again not a solution. But in case of the batteries where you need to charge over a month time or over a year time, those actually will again come down more and more. So then in these cases, you can use your harvester to overcome the limitations of the battery or overcome the capabilities of the batteries. So those are the case for these sensor nodes. So sensor node, as I said, you need to charge it, maybe replace the batteries maybe in few months time or in a year's time. So for those cases, actually your energy harvester, we can clearly see that can win. So volume is again a very interesting parameter here. So if you take a bigger volume, all your energy harvesting capabilities are winning here. As you scale down the volume, your frequency become important. If you scale down, maybe at higher frequency of operation, your harvester are winning. At lower frequency, your harvester are losing. But that's the main research area, right? So how you can operate at the lower volume, lower frequency, and still can take this curve up so that you can compete with the battery. So that's the main research aspect of this mechanical energy harvesting area. So so now comes to the applications. As I said, IoT is the main application area, and IoT can be implemented in different areas like environmental monitoring, or different environmental condition monitoring, integrated biology solutions. In military applications, mechanical energy harvesting could be a very attractive solution. So we are discussing with DRDO, for example, for a project regarding mechanical energy harvesting capability for military solutions. So that's one very interesting area. Then for automobile is another area. Automobile is a very interesting application area for mechanical energy harvesting. Structural monitoring, bridge monitoring, and all are employing energy harvesting, large energy harvesting devices for a very long time. So MEMS could be a good potential for these areas also. So similarly, surveillance could be another interesting approach. And finally, medical remote sensing is definitely going to be the main focus area or the core application area for many of the energy harvesting applications. So, for example, this pacemaker powered by energy harvesting device, mechanical energy harvesting devices, has been shown in some of the recent research papers, and this can be only extended to different kind of artificial prosthetics and all those which upcoming areas are this health monitoring. In those areas, this energy harvesting can be used for some self-powered wireless sensing applications. So this is the application area of IoT for energy harvesting. So let me just go through a couple of other slides and then I will conclude. So energy harvesting is definitely good, but for implantable devices, for example, so if you want to implant some device within your body, then inside your body there you don't have much energy ambient sources, like maybe your blood is flowing, that's a source of mechanical excitation, or maybe your heart is pumping, that's another. But inside your body there is hardly any source of mechanical excitation or any form of energy excitation. So an upcoming strategy is to use energy harvesting from the outside of your body and then transfer the generated energy inside your body using a wireless power delivery mechanism. So for that, we are now working on a magnetoelectric material-based devices. So this magnetoelectric device, actually till now we were considering only magnetic and piezoelectric separately. This magnetoelectric effect actually has a composite effect. So this is a heterostructure where you have a magnetostrictive layer, and on below of that there is a piezoelectric material. So piezoelectric material, we have already discussed what it do. Magnetostrictive is a special class of magnetic materials where under this mechanical strain there in the other way, when you apply a magnetic field, the domain shape change occurs, and as the domain shape change occurs, it gets strained, mechanically strained in one particular direction. Maybe it can extended in one particular direction and it get contracted in the other direction. This thing happens to this particular class of magnetic material called the magnetostrictive material or magnetoelastic material. So for example, this cobalt iron or nickel or iron gallium boron, these are very good magnetostrictive material. So once this magnetostrictive material under the influence of this magnetic field produce a mechanical strain, the bottom lying piezoelectric layer actually convert this mechanical strain into an electrical potential signal. Okay, so then we can use this kind of device. If we can integrate it with the MEMS devices, we can use it for a lot of applications. So this is a conceptual diagram of a MEMS-based magnetoelectric transducer. So here you have an incoming AC electric field. The magnetostrictive layer sense this changing magnetic field, incoming magnetic field, and this magnetostrictive layer sense this magnetic field and convert it into the mechanical strain. The piezoelectric layer convert this mechanical strain into a electrical potential. So we can convert an external magnetic field into an electrical signal. So it has applications. So first of all, if we can, it can act as the receiver for your wireless power transfer technique. So if you can transfer your electrical energy in the form of a magnetic signal from outside your body, then it can act as a receiver for your this wireless power transfer. It can also act as a antenna for communications, which is very important nowadays. And the good thing about is that it can reduce the size of your antenna, because most of the antennas work on this electromagnetic resonance principle. Where you have electromagnetic resonance, then your
the device size has to be comparable with the electromagnetic wavelength, and then it is actually quite big. But if you work at a or if you work with this electromagnetic resonance, the frequencies at which this work, the wavelength that you get is actually quite big, and the antenna size are normally quite big. But if you work on this acoustic resonance principle, then you have this acoustic resonance, you work at this sound wave frequency, and your whatever wavelength you get is actually exactly in the scale of your micro or nanoscale devices. So then this principle can reduce the size of the antenna, and you can get a miniaturized antenna inside your body for communicating with the outside. And third and upcoming application area is the brain signal detection. That is, it can act as a wireless neural interface device, because it is detecting very low, maybe a picotesla magnetic field. So those are your brain actually generates very tiny magnetic fields. So if it can sense those brain activity through these magnetic signals, then we can use it for brain signal detection, and we can use it as a wireless neural interface device. Okay, and the last thing we are working on is this permanent magnets for MEMS or microfluidic devices. So good thing about magnets is don't require any external power for its operation. So piezoelectric device, you need to actuate it, you need to provide voltage to piezoelectric layer to actuate this piezoelectric layer. For electrostatic also, you need to provide outside voltage to change the capacitance. But magnets, permanent magnets, they always generate magnetic field. You don't need any external power source. So this could be a very good solution for zero power actuation mechanism. And zero power actuation mechanisms are very important for microfluidic applications, for different bio-related applications. Maybe if you want to remotely control some medical nanoparticles for cell manipulation, maybe cancer cell manipulation, you need to control your nanoparticles. So what you do, you mix your drug particles with the magnetic nanoparticles, and you use your magnetic structure, permanent magnetic structure along the device in such a way that they get actuated and they get moves along the channel, microfluidic channel. So that kind of capability can be developed using developing permanent magnets at MEMS scale. But developing permanent magnets at MEMS scale is not so easy, because if you take a thin film of magnet, due to the demagnetization effect, what happens is it loses most of the magnetic field coming out of the material. Only the magnetic field that is generated are along the edge of this thin film. So rather we are working on some pattern, micro pattern magnetic structure. So this is a fabricated micro pattern structure also. So what we do here is by patterning, we are increasing the number of edges of this along the one line. So you can get continuous change of magnetic field. So we can increase the average magnetic field over it. So we can use this kind of magnetic structure for different microfluidic application, as I said. And right now what we are also trying to do that could be again an improvement over this is till now all this magnetic structure are polarized or magnetized along one particular direction. But if we can have different magnetic magnetization direction within a same substrate or in a same device, then we can actually increase this magnetic actuation capability of this permanent magnet. So right now we are working on some of the innovative mechanism on that. So this could be a very good zero power actuating mechanism for different microfluidic or biomedical applications that we are currently focusing on. So as I said, so this is the technical talk. So that's where I would like to conclude. So as I said, we are working on different power related applications in our group. So one aspect is definitely power generation, then the power delivery for implantable devices, and then the zero power sensing and actuation mechanisms. So this is kind of the spectrum of work of our group. So if any one of you is interested to know more about our activity or want to work with us in any form, so you are more than welcome. Please contact me anytime. So thank you.
Thank you, Professor. Thank you for your wonderful session. We have got idea in MEMS and also IoT. We have, and also what is energy harvesting. What are all the applications we can do? All those things we have got idea. And we have some queries. Two questions from our participant side. The one question will be the in MEMS piezoelectric energy harvester. Which type of connections are more efficient? Either it is parallel or series.
So in MEMS piezoelectric, so you see the kind of connection actually it depends on. So first of all, the piezoelectric energy harvester, as I said, produce more voltage. So already you have more voltage, good amount of voltage coming out of your device. The current is low for piezoelectric energy harvester. So by connecting different piezoelectric energy harvester in parallel, you can get the same voltage, but you can improve the current. So that's the kind of approach you can take. But normally current is not a very big concern. So normally you get even micro amp kind of current out of your piezoelectric device, which is fine for most of the modern day electronic devices. That is fine. But for you get, if it is small, you can connect them in series to increase the generated voltage. But if you connect them in parallel, your current will get multiplied, but that is not needed. So I think you can connect it in series to increase the voltage if your out voltage level is small.
Professor, we have one more question.
Yes.
Electromagnetic generator, how much current can produce?
So in electromagnetic now, as I said, because its impedance is low, so it produces high current. So for MEMS electromagnetic, again, as I said, MEMS electromagnetic, the current is high, so it may be in the order of few hundreds of microamp. Whereas for piezoelectric, it's in few microamp. For electromagnetic, it may be in the range of few hundreds of microamp, but it is still a high current, considering we are working in the MEMS region. For bigger devices, bigger electromagnetic energy harvesting devices, the current is in the range of milliamp.
One more question we have, Professor, that is RF harvesting is to be used in 5G mobile technology. Any possibility in your work? Like that they are asking.
Sorry, I can't hear the question properly.
RF harvesting is to be used in 5G mobile technology. Any possibility in your work? They are asking.
Yeah, so right now we are not exactly working on this RF energy harvesting. As I said, this RF energy harvesting, there is definitely some scope to work, but not much from the device aspect, because our group's focus is mainly on the related to someone or the other in the device area. So we are not currently focusing on the RF energy harvesting. But yes, I have few innovative concepts where we can actually miniaturize the size of this RF transceiver devices, which can be used for RF energy harvesting application also. I think it can be utilized for the upcoming 5G or even newer technologies as well.
Actually, we have got very good feedback here, Professor. That is, your areas is very interesting, and also they are very interactive. It is what we have to tell. It is a presentation. Your presentation is also very good, and they are asking to share your PPT, this thing and all. They have shared in chat box. Thank you, sir. Thanks a lot for spending your time with us, Professor. Thank you.
Okay. Thank you. Thanks a lot.
Thank you, Professor.
Thank you.
Participants, tomorrow we have again we have the two session. One change will be the tomorrow the session will be started by 11 o'clock, which is handled by the Dr. Gupta sir from IIT Roorkee. Afternoon session going to be handled by Dr. Murugan. She is an industry person from Western Digital. So tomorrow this will be the only change. Tomorrow morning session you have to join by 11 o'clock. So tomorrow will be the last day. We need your cooperation to complete our FDP successfully. Kindly join in a proper time. It will be it would help to complete our session tomorrow successfully. Thank you all.